Okay, good morning. Sorry for the delay. No, rain is creating a bit of delays in everything. Okay, so we are done with many things in the unit in the course till now. So we have done with beams, done with slabs, done with some special, not special, some specific structural elements like flat slabs and staircase also. So all these things are covered till now, and we are now nearing the last part of our course. Okay, which is columns and somebody, your camera is on, please turn it off. Thank you. So now coming to columns. So what is the difference between a beam and a column? What? I mean, there are many differences. You can tell one by one.
It is a vertical member.
A vertical member, okay. Then?
You take compressive load.
You take compressive loads. Okay, good. How about anything else?
It will also take lateral loads.
They also?
Take lateral loads.
They can take also lateral loads in addition to taking the axial load. Okay. So in general, these beams and columns, they are very specific elements which take only a certain type of load. Okay. So for example, if it's a beam, we generally mean that it takes only transverse loads to its axis. If it's a column, we assume that it generally takes only loading through its longitudinal axis. Okay. But that is only very specific ideal definition of beam and column. But there are cases where column also can take moment in addition to a compressive force. Okay. And similarly, a beam also, it can be undergoing a lot of bending, but there may be sometimes axial forces on beams. Okay. So in these kind of situations, we call them as beam columns. But in general, when we want to say, when we want to identify a column, we just see whether there is an axial load. Okay. If there is an axial load, then we just call it as a column, irrespective of whether it has bending moments also. As long as there is axial load, we call it as a column, and if there is no axial compression or axial load on that particular element, then we say that it is a beam. So this is the general way that we identify them. So the main difference is in loading direction with respect to the member axis. Okay. In general, in normal buildings, we see that columns will be oriented in the direction of gravity. Okay, meaning vertical, like you said. Okay, so that is a general orientation of a column. There may be some situations where your column may not be oriented in the gravity direction. For example, sometimes you may have a frame which, for example, you have a truss. Okay, whenever you have a truss, you don't have all the elements which are vertical. They will be inclined, they will be horizontal, etc. But some of the inclined or horizontal members also will take only compression. Okay, so in that case, it is not oriented in the direction of gravity. So this kind of, it's not called as a column. These kind of elements which are inclined or horizontal, but still they take compression forces, axial compression, we call them as struts. Okay. In general, but RCC, as far as since we're dealing with RCC here, in RCC generally for normal buildings, we see that columns will be oriented in this particular direction. They are the final objects resisting load, and hence always a good design has strong columns and weak beams. This word weak is actually relative. It's not an absolute term saying that the beam has to be weak. Nobody wants anything to be weak. Okay, nothing should be weak. But when I say strong column and weak beam, we say that in relation to the column, the beam is weak. Okay, the reason why this principle is adopted usually is if your beam is really strong and the column is weaker than the beam, then you will have a situation where the beam may be perfect, nothing has happened to the beam, but the column may fail. And if the column fails, it's only above the column that everything exists. Only above the column the beam is there, and on the beam the slab is there. So if the column goes, everything goes. However, if column is good enough and something else like the beam or slab is failing or whatever, then at least that can be fixed. Okay, but if column can also be fixed, but it's a little more dangerous if something happens to the column, because they are the final resisting load resisting object. So this is what I mean. This is the flow of forces in this picture. So you have the load acting on the slab. From the slab it goes to the beams on the perpendicular edges, and from the beam they flow down to the columns. And if the column goes, everything about goes. Okay, so that's why we take the principle known as strong columns and weak beams, meaning that in an absolute sense, we don't mean that in an absolute sense that the beam has to be weak. Nothing should be weak. It's a relative comparison. So how do the columns fail? Okay. So you see that, for example, this picture here. What is happening in this picture? What is this? What are you seeing in this picture? Is it a column or what is it? What is this thing?
Compression test.
Compression test. It's a basic compression test on a cylinder, concrete cylinder, to find the grade of concrete. Okay, so that's what this is. So what do you observe about the failure of this cylinder?
Shear failure.
Oh, yeah, it looks like shear failure, but it's not shear failure. It looks like shear failure because it is inclined. In this particular case, the crack is inclined. It doesn't always have to be that way. Okay, it's not shear failure. There is no possibility for shear to occur. It's axial load. Any shear will be very, very less than that. It's actually perfect compression. Anyway, it's crushing failure. In this picture, it looks like shear failure. That's it. It's crushing failure, and this is under perfect compression. Okay, a column is also something which takes pure compression. And in general, for a cylinder test, what is the dimensions of the cylinder? Anyone remembers what the dimension of a cylinder should be for testing?
Height should be 2 times of the diameter.
Height should be 2 times of the diameter. Okay, or it's just imagine that ratio. Height by diameter is about 2. Okay, so we see that this one, wherever we have low values of height by diameter, okay, a small value of height by diameter like 2 or 2, 3, in that range, okay, single digits. So whenever we have such a ratio between height and diameter, we call, there's a specific limit, I'll come to that, but as of now I'll just tell that the ratio is low. At such low ratios of height by diameter, we call that column as a short column, and the short column will always fail by crushing, like how this cylinder has failed. Okay, so for example, this column over here, you see that this is a rectangular column or square column, something maybe about 500 mm or something. It's having that lateral dimension. So probably this whole thing may be about 3.5 meters or 4 meters, a little more than 4 meters, I suppose. So this ratio is about maybe 8 or something. Height by the lateral dimension is about 8 or 7. I don't know, something like that. So we see that this also has crushed. Okay, this column has crushed. The concrete and all has spilled out. You can see the reinforcement cage inside and all. Okay, so this is known as a crushing failure. Any short column will fail by crushing. However, when I look at this column, this diameter, if it looks like maybe 500 or 300, whatever it is, this column maybe, I don't know, 6 meters or more than that height. Okay, so it's quite long. Okay, So the height by diameter ratio is quite large. It's not comparable to the height by diameter ratio which is present in this picture, or height by lateral dimension. If it's a circle, it's diameter, otherwise it's the shortest lateral dimension. So this is a long column, and how does this failure of this column compare to the failure of this particular column? What is the difference between this column, how this column has failed, and how this column has failed? Both have failed under pure compression only, axial compression, but it looks different. What's the difference? What is the difference in the way this looks and this looks?
There is a bend in between.
It has?
In the figure.
Tell again.
So in the second one, there is a buckling at the center.
Buckling at the center, okay. Or basically, you see that there is a little bit of change in shape. It's not straight anymore. Okay, it's no longer straight. So, for example, when the column was perfect, this red line, it should have been straight. But now you see that this red line is no longer straight. It is, it's kind of curved, or it's changed its direction in both the ends. So this is known as the buckling failure. Okay, you people would have come across buckling. You have come across buckling, right? What is the famous theory for buckling? One very small, short formulas there to find buckling load. Anyone remembers it?
Pi square AB L square.
Pi square AB L square. It's called as Euler's buckling formula. Okay, so the Euler's buckling formula, it is as long as the material is having the proper E value and it is it's a nice elastic material. It's not directly suitable to concrete, but if the column is quite long, it still is applicable. So column crushing resembles a similar cylinder test. Buckling is not observed as clearly as in steel. Okay, because if you have a steel column, you can see buckling very nicely. Okay, because it is a homogeneous material, there is it has nothing else. Okay, but concrete it's a brittle material. It's not a ductile material. Okay, so therefore you can still see some buckling, but it will not be as clear as in steel. And whenever buckling occurs, the concrete can spall off, and once the concrete spalls off, there is nothing to restrain this steel reinforcement from undergoing buckling. So that's what is shown over here. So if the concrete spalls out, then the reinforcement can actually buckle. So this is how we kind of decide how those columns are, what type of columns they are. Okay, these are assumptions that we make in our IS 456 are for the design of columns. So having a situation like this, okay, like shown in the previous slide, where the load is exactly through the centroid. Okay, having a situation where the load acts exactly through the centroid, it will not be achieved in real construction. Okay, practically it is not possible to make it exactly centroidal. Okay, so designing for such a situation, saying that my loading is perfectly axial, making that assumption may not be a very good idea. Okay, so therefore we say that we make that perfect axial loading is idealistic. Okay, which does not always, it's not always possible. It's almost never possible. Okay, for example, these occur due to construction errors, movements, settlements, etc. So for all these reasons, you will not have this situation. So therefore, design based on perfect axial loading is not advised, and we have to adopt a minimum eccentricity. Okay, so what is eccentricity? Eccentricity is nothing but instead of having perfectly axial loading, how much away from the centroid do I take the load to act? Okay, so if this is if it's a circular column, it could also be a square column. If it's a circular column, So instead of acting through the centroid, how far away from my centroid is the load acting? So that is known as eccentricity. So how much should I assume is the eccentricity? Okay. And once again, every single column, every single building, this eccentricity will not be same. Okay, it's not possible to know the eccentricity also. But something we have to assume so that we can do a proper design. So the quote helps us there, saying that based on several studies and based on some rational approach, they have specified the code that you can assume this value as the eccentricity, okay, as the minimum eccentricity. Okay, so the eccentricity, what they have decided is the eccentricity is dependent on the length and size of the column. Okay, length means the length, size means height by width, the width by the breadth or diameter, whatever it is. Okay. So how much is it? So it says that all columns shall be designed for a minimum eccentricity equal to the unsupported length of the column. Okay, that's the keyword. The unsupported length of the column plus, unsupported length of the column by 500 plus the lateral dimension of 30. And we find this out, and if it is lesser than 20 mm, we say that the minimum eccentricity should be about 20 mm. Okay, so this is how we do that, and we also make a comparison or a classification between short and slender compression members. So this short and slender compression members is what I showed in the previous slide. Short compression member means it's going to feel like a sling, it's going to crush. Slender or long compression member means it is going to fail by buckling. Okay, so to identify this, we have we take the the length along both the axis, x-axis and y-axis. Okay, divided by the lateral dimension, either diameter or breadth or whatever it is, and then if it is less than 12, if this ratio is less than 12, it is a short compression member. If it's greater than 12, it's a slender compression member. Okay, so there's one key difference between RCC columns and steel columns as far as this definition is concerned. So this slenderness ratio which we define over here, if you see in concrete members, it is length by some dimension. So this is how it is given for concrete members. If it is steel member, it will not be given like this. Okay, the slenderness ratio will be given by L by something called as R or radius of gyration. Okay, so I think you people should know what is radius of gyration. Do you know what is radius of gyration? What is radius of gyration?
So from that mass moment of inertia we can calculate.
Yeah?
From that mass moment of inertia.
Okay, yeah, with that, for the moment, not mass moment of inertia. Moment of inertia and what? So basically, moment square root of moment of inertia divided by area of cross section. That is radius of gyration. So for steel members, they use L by R. Here they don't use R. Rather, they directly use the lateral dimension DRB for concrete members. Okay. So we are assuming a minimum eccentricity. So this minimum eccentricity causes a moment. So why does it cause a moment? Basically because we have a load, and this load is acting at an eccentricity. Okay, it's acting away from the center. So this load times this eccentricity, that causes a moment. Okay, so this minimum moment, whether we need to worry about it or we do not need to worry about it, is given by a certain criterion. I think maybe I'll have to do that tomorrow. But anyway, so these are some other aspects of columns. So if you have a comparison between axial load and axial strain, so this is steel. Load strain. Okay, load strain curve. It's not stress strain. If it's a stress strain curve, then this for steel it will be much big actually. This is load versus strain. So we see that for concrete it goes up, achieves some value over here and then comes down. Can you even guess what the value of strain at this point is? What is the value of strain at this particular point? The peak. Any guesses based on your first unit? What is the strain corresponding to this point?
0.0035.
0.00 not 35. Some other number.
2.
0.002. That is the ultimate strain in concrete in compression. Okay, yeah, good. So anyway, so then we look at the reinforcement. This is how they look. So you have longitudinal reinforcement at the minimum. You have to give it at the corners. If it's a square or rectangular column, if it's circular column, you need to give minimum of 6. Okay, for a rectangular column, minimum is 4. For a circular column, the minimum is 6 longitudinal reinforcements. And of course, you have to give ties. Okay, these look like stirrups, but they are not stirrups. The function is not the function of a stirrup. Okay, so these are known as ties, even though they look the same as the stirrups. They look the same way. But the purpose of giving this tie is not. It's not exactly for shear.
Yeah, that's, I mean,
So they can take shear.
can you go to your envoy?
Sivaram, please mute.
Can you, this one, can you scroll up? Oh, okay, cool. Just a second.
Okay, so here in a column, the reason for giving tie is not the same reason as for giving for a shear, though the tie can serve a double purpose of taking shear also, if there is bending moment in the column, or sorry, if there is shear force in the column. So the purpose of the tie is basically, okay, anyway, let me not tell the answer. What do you think is the purpose of this tie? So we have a longitudinal vertical standing reinforcement bar at the corners, and at every certain distance, every certain height, you are giving some ties. What do you think is the reason for giving this tie? What purpose does it serve? Some answer. Any answer is okay.
To resist buckling.
Against buckling of what?
Column reinforcements.
Yeah. Basically, I mean, yeah, you're almost right. Basically, it is for. So you have this reinforcement. Anyway, you're filling concrete. Okay. So after filling concrete, anyway, the concrete around the reinforcement itself will make sure that the reinforcement does not buckle. Okay. But it serves two purposes. It keeps the longitudinal reinforcement together. Okay. And the other thing is, when somebody is constructing a column, so what you do is, they'll make the formwork. They'll first place the reinforcement. Okay, before placing the concrete. So that time, if you don't give these ties, those reinforcement will just be just moving about like they wish. So to make sure that they are in place, they give the tie. So it basically, so this is visual thing that you can understand about giving a tie. But technically speaking, how you say the purpose of a tie is, it confines the concrete. Okay, the word is confinement. So this property called confinement is it's a very useful thing for concrete. When concrete is confined, you get a little bit of advantage in its compressive strength of the particular column. The column which you have, if you achieve good confinement by giving the ties, it will have some benefit in its compressive strength when you have confinement in the concrete. So this tie actually helps the concrete to get confined. This confinement is much more beneficial when you have a column which is not separated, when you have ties which are not discrete like this, but if you have a spiral tie, like shown over here, you see that these ties are not single ties. It's the same tie which is going around spirally. So whenever you have spiral ties, you have even more advantage through the confinement. However, spiral tails can be given only for circular columns. For circular columns, it cannot be given for rectangular columns. Okay. By the way, don't get confused about this formula. I just wanted to show this picture, but this formula is from it's according to American code, but not IS 456. But anyway, the picture is same. The shapes don't change. Okay, I think this I'll have to cover tomorrow because it will take a bit of time to explain. Okay, so these are some introduction to columns. And so I've uploaded the PPTs with regard to